My name is Brandon Trabucco. I'm a PhD student in the Machine Learning Department at CMU, advised by Russ Solokudinov, and this project was a collaboration between our lab and a team at Amazon, including Gunnar Sigurdsson, Robinson Piramuthu, and Gaurav Sukhatme. Today I'll be presenting a simple approach for visual rearrangement, 3D mapping, and semantic search. Rearrangement is a challenging task that involves an embodied agent interacting with objects in its environment to reach a goal that can be specified in a variety of ways. Visual room rearrangement is an especially hard instantiation of the rearrangement problem because the goal state is not explicitly given to the agent. Rather, it must be inferred from the agent's experience during an episode by the agent remembering what the environment looked like. We will focus on the two-phase visual room rearrangement problem, where an agent observes an indoor scene in its goal state during an initial walkthrough phase, and the agent is then placed in a new scene where up to 5 objects are moved, and the agent should modify the scene to match the goal state observed during the walkthrough phase. The agent's goal during this secondary phase is to maximize its success rate, defined as the success rate that the agent successfully rearranges every object in the scene to a desired pose. Rearrangement is a challenging task, and our key insight to solving it is to build voxel-based maps for each phase of the environment and to reason about what objects need to be rearranged by finding those objects in the maps. Our approach has 3 components. First, we build accurate voxel-based maps of the environment. Then we learn a search-based policy to efficiently find objects and populate the maps. And finally, we rearrange the scene by locating objects, moving them to the goal, and placing them at the goal until the agent predicts that all objects have been rearranged. Building accurate semantic maps is crucial to our method, and this is challenging. It requires processing images of the scene from multiple perspectives. We approach this challenge by incrementally back-projecting egocentric semantic segmentation predictions from a pre-trained mask RCNN to a set of voxels at each time step, capturing the state of the environment during the walkthrough and the unshuffle phases. Building accurate maps requires finding objects in the scene that need to be rearranged, and we approach this challenge by training a semantic search policy, pi, that parameterizes a distribution over search locations in the scene that are likely to contain objects that need to be rearranged. Once accurate maps are built, MaSS determines which objects to rearrange by identifying disagreements in the maps and iteratively rearranging those objects until no disagreements remain. And together, these components let MaSS efficiently solve two-phase rearrangement problems, which we discuss next. MaSS significantly improves two-phase rearrangement. Our method improves 31 times over the most recent baseline for two-phase rearrangement that uses end-to-end RL, called VRR plus map, in the table, despite requiring only 2.7% as many samples from the environment. MaSS solves 47 out of 1,000 test set tasks, leading to a relative improvement of 1,175% over a recent baseline CSR. In addition, our semantic search policy accounts for 275% of the observed performance gains, and our results confirm that planning-based approaches, which include CSR and our method, can improve both performance and efficiency on visual rearrangement problems. Our results with MaSS improve even further when replacing our perception and search modules with experts. Compared to the recent baseline CSR when given expert instance segmentation and expert search goals, our method improves by 1,742% success on the test set and rearranges nearly 60% of objects correctly in the test set. These significant gains with expert perception and search show that building accurate semantic maps is important for visual rearrangement problems. We presented MaSS, a solution for visual rearrangement problems using 3D mapping and semantic search. MaSS is trained offline and uses planning with voxel-based semantic maps to rearrange objects. Our results show that MaSS is efficient, improving by 1,175% on prior work and over 31 times over the leading end-to-end RL-based approach on the leaderboard. The success of MaSS on the rearrangement challenge suggests a few directions for future work. First, we observe that MaSS significantly benefits from expert perception and search models. Improving map fidelity with better models is therefore an important way to further improve the efficiency of MaSS. Similarly, our mapping approach relies on accurate pixel depth to back-project semantic predictions to the map. Generalizing our method to settings with noisy depth observations and imperfect localization is then important before MaSS can be applied in the real world. And finally, combining the advantages of our approach with the advantages of reinforcement learning could help give policies spatial awareness and the ability to reason about 3D objects. My name is Brandon Trabucco. It's been a pleasure presenting to you, and for more information, read our project website or get in touch. Thanks for listening.